So, I'm Joshua Wilson. I'll be presenting to you today on next generation neural implants and some of the ways that we can make them survive longer in the body. Yes. So for the contents of the talk, firstly, I will introduce the technologies for Bioelectronics team, the team members, and our motivation in the research that we do. And then I'll go into detail about different coating investigations, the strategies we can use, and what materials we like to use. And finally, I'll sum up, give you some key takeaways, and thank everyone who needs to be thanked. So about the technologies for Bioelectronics team. We are based here at Fraunhofer IZM in Berlin. Here you see us, which is 7 people at the moment. We are also supported by a small number of students, and the leader of this team is Vasilka, and she also has a position at TU Delft in the Netherlands, where she is a professor, and so we are also working very closely with them, integrated as one team, to use both facilities and all the expertise of all the team members to achieve our goals. Now, as we all know, most of modern medicine is reliant on pharmaceutical drugs. Everyone takes these pills when they are told to by the doctor, and this has been largely very successful for a very long time. But there are many conditions which cannot be treated with such pharmaceutical treatments. So, for example, treatment-resistant depression, blindness, spinal cord injury, rheumatoid arthritis, the list goes on. So we need to find another solution. Now, one option is to communicate with the nervous system using electronics. In some cases, you can achieve the desired result with non-invasive methods, for example, transcranial magnetic stimulation. But if you look at this image here, you begin to understand some of the problem. In green, we see neurons, and you see that they form a very complex network. And the feature sizes here, so the critical feature sizes of these neurons are on the scales of tens of microns, and there are billions of these. So what we need to, in order to prevent off-target effects, is to be very specific. Maybe we want to stimulate this neuron here, we don't want to stimulate this neuron over here. And this means effectively that we need to go inside the body to raise our chances of being more specific. And the downside of this, as you can see, is that this involves surgery. And this is highly invasive. There are downsides for the patient. Here you see a cuff electrode wrapped around the vagus nerve in the neck. I'll talk a bit more about this system in a minute. And so ideally, we would like to only do this one time. We don't want to have to go in and take the device out, replace batteries, things like this, because every single time you do this, there is a risk for the patient. Now let's have a closer look at the standard design of some of these implants. So here is an example of a vagus nerve stimulator, but the structure of this system is very similar for throughout other systems, for example, DBS. Firstly, you have this round hermetic can. This package is made of titanium, and it houses most of the electronics. And this has some feed-throughs, and this whole central part here is implanted somewhere near the shoulder. And these feed-throughs pass out to a lead, and this lead runs up the neck and ends up at this cuff electrode, which wraps around the vagus nerve somewhere in the neck. So the problems you see here is this is very large, and that it has to be kept quite distant from the tissue that you want to interface with because of the size. This introduces additional complications. We need this lead to travel all the way there, and this can be failure prone, and this is another problem. Now, there has been a lot of work done to reduce the size of such devices. This is one example from the Texas Biomedical Device Center. Here they've reduced this hermetic package to a much smaller dimensions. You were talking about millimeter scale, whereas you're talking about centimeter scale on the left. And this will reduce the discomfort for the patient, takes up a smaller volume, but still you are using this hermetic package. And the problem here is if we start to look at the material side. So in terms of material properties, on the left-hand side here, this is a line with all of the different some different materials with different Young's moduli. And what you see is on the left, the materials are very soft, and on the right, the materials are quite hard. And you see that these titanium and glass housings fall very much to the hard and stiff end of the spectrum. And the problem with this is that when there is micromotion, such materials can damage soft tissues like the gray matter in the brain or any neurons any peripheral neurons. So ideally what we want to have is implants from softer materials. Now, so just to summarize our broad aims from these few slides of motivation, firstly, we want things to be small. Small things take up less space, they reduce the patient discomfort, they are effectively less invasive. We want them to be soft, so we want our system to have a reduced mechanical mismatch to the tissue that we're implanting in. We need them to be safe. The patient safety is always the first priority. We should always use biocompatible materials. We should adhere to strict regulatory standards. And then, as I mentioned, we need to be very specific. The reason that we're doing this is, well, one reason is to reduce off-target effects. And if we aren't specific, we won't be able to do this. And finally, the body is a very harsh environment. You have water, you have salt, you have oxidative stress from immune responses. And so we really need these devices to have a high level of survivability. They need to endure inside the body for years and decades, not weeks and months. With all of this in mind, we focus on several core areas to achieve these goals. So firstly, the focus of the talk today will be on the packaging technologies for these bioelectronic implants. This is one area that we focus on. Another is integrating and interconnecting components on biocompatible polymer substrates, so these soft substrates. Then more away from the materials side, more towards the electronics, we are looking into electrical and ultrasonic neuromodulator system design. So the nervous system we can communicate with electronically. This is the standard implant method. Think about pacemakers. But we can also communicate with neurons using ultrasound. We can stimulate neurons with this, and this has a distinct advantage, which is that you can focus ultrasound, and this allows you to be more precise. And finally, we also work on ultrasound power transfer and communication. Here you see our ultrasound characterization setup with a water tank and transducers. The advantage of the power transfer using ultrasound is that you can go deep into the body. Ultrasound is also very well known in the medical field. And so we can achieve with this there's the potential to achieve with this smaller implants deeper inside the body. Okay, so coating investigations. First, I will start with some general learnings. Don't get bogged down on the specific materials at the moment. I will clarify when the materials become important. So when you want to put an electrical system, an electronic system inside a human in a very wet environment, you would imagine that a good thing to have to protect your electronics would be a water barrier. And so we have here in the table on the left-hand side a set of materials stacks. These are polymeric materials, and we measured the water vapor transmission rate through these. So the amount of water that is passing through over time, these thin materials. And what we see is we go down the table, the amount of water that passes through is reduced. Okay, easy. Another thing we investigated is the adhesion of these materials to the substrate. And it's the same material, same table basically. And what we see is the opposite trend. Now, when we tested our test structures in a long-term soak test, so we soak them in saline solution for months and years, and we raise the temperature in order to accelerate the degradation process. What we saw was that the devices that survived the longest were the ones that had the best adhesion to the substrate. So what can we conclude here? The water vapor permeability isn't the main factor determining the lifetime of these devices. The key is the adhesion, and I will try and hammer this home throughout the presentation. Now if we turn our attention to an example system, so this is just a schematic of how maybe one of these future neural devices will work. We will have a coil because we want it to be battery free. We don't want to replace the battery, and we also want it to be small. So we have something like a coil to receive energy, maybe to transfer data in and out. Then we have maybe some kind of energy storage, capacitor, supercapacitor, something like this. And here in the center we have an IC. This gives us power management, the intelligence to have stimulation regimes and recording, which connect to our electrodes, which interface directly with the tissue. And in each region of this overall system, we have different electronic signals. So with the coil, we have an AC signal. With the capacitor, say, we have a DC signal. And if we're doing stimulation, these tracks to the electrodes will see this typical biphasic signal, which is used for neurostimulation. So what we investigated was what happens if we use different signals on our test structures. Will the results be the same? And in fact, the answer is no. So in one case where we applied DC, we saw crackling of the coating. And in another case where we applied biphasic signal, we saw the metal dissolving, corroding, migrating. So what this tells us is the failure mechanism of the device is also dependent on the stress signal. So whichever signals you have in your device, these are going to affect the failure. And then based on this, we look at the IC, because the IC is the place with the highest electric field. And so potentially this is an area where the failure could be fastest. So we built some test structures inside an IC in different layers. So we have some interdigitated capacitors, we have some transistors, we have some dielectric sensors, and we connected it up for soak testing. And we soak this at 67 degrees, so it's again accelerating the failure by increasing the temperature, accelerating the potential failure rate by increasing the temperature. And what we see is everything is stable for a year. So what this tells us unexpectedly is that actually the CMOS is electrically stable for a year after accelerated aging. You don't need to do much at all. But if we look more deeply, if we don't just look at the electrical characterization and we look at the surface of our devices, what we see is for the devices which were biased with this 5-volt DC, we see some degradation around the edges here. And this matches where the electric field is highest in the top layer of our chip passivation. And so what we think is happening is what we know is happening is that the 5-volt DC bias combined with this saltwater environment is driving a degradation of this chip passivation. So in these wet environments, the CMOS passivation, while it endured electrically for a year, the passivation is already starting to degrade. So how can we improve this? So one hypothesis is to introduce a shielding layer. What I mean here is that in the devices that degrade, what we have is these two metal lines in black, and we have an electric field that passes between them. And this stray field can reach out into the body fluid, and this can drive some degradation process. But if we introduced a metal layer, additional shielding layer, all these field lines would terminate here, and there would be nothing to drive this process on the surface. And in fact, what we see is that if we use this shielding, we see that there is no change on the surface of the silicon nitride in comparison with the other devices which didn't have shielding. Another hypothesis was that, okay, this is DC. What we already saw that the failures were signal dependent. What about if it was AC? And what we see again there is that there is no failure. So if we use AC in the top metal layer rather than DC signals, we don't see any failure. And actually, you see in the DC stress device here, the failure was very fast. After 2 weeks, there's cracks in the coating, and the metal is corroded. So a conclusion would be that the shielding and AC electric fields in the top metal layer can lead to longer lifetimes of these ICs. Basically, what we're proposing is IC design specifically for these non-hermetically encapsulated devices. So these very thin film polymeric encapsulations. If you design your IC in a certain way, you can increase the lifetime. Now, maybe this is a bit complicated, and you prefer just to stick with coating of these uncoated devices. So if we look again at this this chart of the Young's modulus, we see I've added a bunch of different perspective materials. One here is silicone, and this is the softest and is well known and often used in the medical field. And so what if we encapsulate our device with this material? Now, so here we took the device. This is the silicon nitride surface, and this is a silicone, and so it's only partially coated. On the left hand side is coated, on the right hand side is not coated. Now what you see here in a cross section of this device is that the area that is coated, there is not very clearly any degradation, and in the area that's uncoated, exposed to the saline solution or the body fluid, you see some degradation. Now, how much degradation exactly? If we do a depth profile of these different areas, what we see in the area that was fully exposed, we saw 130 nanometers, 120, 130 nanometers of oxidation of the silicon nitride, and in the area that was coated with the silicone, we only see 12 nanometers. So what does this tell us? This tells us that by coating with silicone, we can increase the lifetime by up to 10 times. So silicone can really slow down this oxidation or damage of the chip passivation. So now that we know this, we can propose effectively a roadmap for protecting these ICs. So if dependent on what lifetime you desire. So if you only care about having your device in the body for 1 year, then okay, a bare chip will work. And if you adhere to some basic design guidelines, then you will be fine. if you go up to a decade, if you want to go up to a decade, then you introduce this PDMS silicone coating, then you should be fine there as well. But if you really want to push it into several decades, then you need to coat the device and also follow some special design rules like these shielding layers, and also this using AC signals in the top layer. So what we see here really is a synergy between the materials science and the electronic design, and you need to think about both when you're doing your design. And also what we see is that miniaturized non-hermetic encapsulated neural interfaces can have long lifetimes. Now, what I spoke about so far is only coating the chip, but typically the trend is towards much more complex systems than just a simple chip. And the problem with using silicone is that it's incompatible with a lot of clean rooms, and this limits your ability to use advanced assembly, packaging, photolithography techniques. So if you really want to have miniaturized implants, then probably you're going to need some of these technologies. And a good alternative option, we feel, is thermoplastic polyurethane. This is also medical grade, very commonly used. It's very soft as well, not quite as soft as silicone, but very soft. And it's compatible with microfabrication, which is very important. Now, if we take a look at this polyurethane, if we start to build a device, then we will have a TPU, a thermoplastic polyurethane substrate, and we will do some lithography processing or something with some gold metallization, and then what we do is we laminate a second layer of TPU on top. And when you build up these multi-layer structures, what you see is you have a lot of interfaces here. So there's a TPU interface, there's a TPU gold interface, and all of these interfaces are potential points of failure. So anywhere where the water can get in and travel towards the electronics to start corrosion, or even just delaminate the two different polymer films to separate them, this is going to destroy your device. So the major advantage of using polyurethane when we laminate it in an optimized condition, when I say optimized, a high enough temperature that this thermoplastic can melt, when these layers are melted together, you remove this interface. So, and thereby you reduce the possibility of delamination and failure. And this material stack is stable in vivo for 6 months, almost certainly for much longer. And we can also assemble chips on these materials. So here you see a cross section with a chip, and what you don't see is the TPU because of the contrast. It's very transparent. But here is, if we zoom in, this is the gold line from above, and here is the chip bump, and we can bring them together and interconnect. So we're able to assemble chips on these structures. And as a proof of concept, we have these devices with 15 micron, very high precision devices, 15 micron lines and spaces, and this chip integration as well. Now, while we really like this TPU process, there is one major difficulty with both this process and several other processes that are deposited using solution. And this is a difficulty coating complex 3D structures. So a solution for this is to use medical grade Parylene C. This is compatible with microfabrication and has long been used since the 80s, and it's deposited via vapor deposition, which is a different method. So to explain the detail of this, effectively, if you were solution processing or laminating a coating on your system where you have wire bonded components, or however you were assembling your components on the surface, what you find is this is slightly exaggerated, but what you find is you don't have perfect coverage. You have some voids. You can't get underneath structures if there are gaps. If you have very fine pitch, then you can have this tenting on, then there are more voids. And anywhere where there's voids, this is just a space for the body fluid to get in and start the corrosion process. So this is really a major point of failure. The difference if you were using a vapor deposition technology is that what happens is that the material is in the vapor phase inside the deposition chamber, and it condenses on the surface, and this condenses all over your device and can penetrate into very small spaces, and so this is what we're getting with a Parylene C. Another additional advantage of the Parylene deposition is that it's possible to combine it with other deposition techniques which are deposited in vacuum. So this allows you to create multi-layered, truly conformal coatings with pristine interfaces, because if you don't break the vacuum of the chamber, the surface is going to be perfectly clean, and the cleanness is really of major importance when you want to ensure that you don't have delamination or defects between your layers. So for example, we can put our sample in this chamber. In what we have at IZM is a combined Parylene and ALD system. So we can deposit Parylene, and then we can deposit these ALD films. So ALD is atomic layer deposition. These are nanometer thin films. They are, as the name suggests, deposited effectively atom by atom. You would deposit a metal layer, then an oxide layer if you were making a metal oxide, and you slowly build it up like this. And what we can then do is add these layers on top, and we can just keep building more and more complex arbitrary stacks of these layers. Now, to explain a little bit the concept behind this, so here is an example of our Parylene ALD films. So we have a substrate, then we have some aluminium oxide, some titanium oxide, and some Parylene C, and this is repeated 5 times. And then you see in the cross section here that is with SEM, that the dark layers here, these 5 wide dark bands, which are 1.3, 1.4 micron thick, are the Parylene layers. And then these very thin lines in between, if we zoom in, these are the 2 ALD layers. So the concept behind this is that the ALD layer is effectively a ceramic, and this forms a water barrier. But the problem is that it's too brittle to really be effective on its own. And so the Parylene offers some kind of mechanical buffer to stop it cracking quite as much, and also from cracking in one plane. So imagine if you had a crack in the ALD that traveled vertically directly through this whole multi-layer structure, then your device isn't going to last very long. Because the water just has a straight line, it will go directly to the electronics, and the corrosion process will begin. What this mechanical buffers do is effectively create a longer, more difficult path, so the cracks are in different places, and it has to travel back and forth, and it slows this process because it's a longer diffusion path. With this as well, though, there is a balance to be struck, because while you introduce more and more barriers, and okay, you delay the water more and more, you have to remember that you were introducing more and more interfaces, and these are more and more places where you can have failure. So there is really a balance to be struck there. Okay, and just to summarize, I'll give you some key points. Firstly, miniaturized conformally coated implantable systems have the potential to survive long term. So this is one key takeaway, but really the biggest takeaway would be the second one. Adhesion is the key for long lifetimes. You really need these things to stick together, because if they don't stick, then you start to have voids where the body fluid can get in, begin the corrosion process, or you can have delamination, which leads to rapid failure of the device. And finally, the material choices really matter. So for your system, you need to select the right kind of coating for the design you have. But this doesn't mean you should go and design your system and at the end just be like, okay, now I need to coat it. Give it to someone else and they will coat it. You need to collaborate and think about how you're going to coat this from the beginning. It's really a two-way street. And so we need to think about how we're going to do the passivation on the electronics while we're doing the design. Okay, and just to thank everyone who deserves to be thanked, particularly the alumni of our group. A lot of this was their work, particularly you may have seen the names at the bottom of the slides, Kambiz and Anna, and also to thank everyone we've worked in with projects, all the funding partners, and all of the current and former MSc students who work with us, who really make this happen. And with that, I will say thank you very much. We would of course love to team up with you. All my details are on this slide here. Again, the QR code you can scan and it will take you to the webpage of our lab. Yeah, thank you very much.